Today, we're going to talk about three existence theorems that are really important for us to be using throughout the rest of our calculus topics that we cover. When it comes to a theorem is just a general statement that has been made and also proven in various ways that we can then use to go and do more complicated problems or verify more complicated problems. If you think about the Pythagorean theorem, stating that for all right triangles, a squared plus b squared equals c squared, we just use that formula whenever we're trying to work around something with a right triangle. We don't actually take the time to go and prove that theorem all over again because it's already been proven. Similar to the three existence theorems that we're going to talk about today, these three theorems are going to help us to verify and move other problems along, but we have to understand what these theorems are and the conditions that need to be met before we're allowed to just say, because of this theorem, we can know X, Y, and Z. The very first existence theorem that we're going to talk about is called the extreme value theorem. When we talk about extreme values, the extreme values are generally referred to as minimums and maximums when we talk about various functions on a graph. So if we look at the three graphs that we are presented with here, we do have a maximum up here in between a and 0, and we have a minimum between 0 and b. For the function in the middle, we do have a maximum that occurs at the endpoint of a and a minimum that occurs a little bit to the right of 0. For the last function from a to b, we don't actually have a maximum or minimum because we start these and end the interval with open circles, or an open interval that we have here. So the extreme value theorem is going after the fact that we can find an absolute maximum and an absolute minimum somewhere on this interval, provided that it is a closed and continuous interval. So for example, the first two functions have mins and maxes, absolute mins and maxes somewhere. It might be at an endpoint, it might be at an interior point. But for our last example, because this is an open interval, we cannot guarantee that we're going to have a min or a max somewhere. So in order for the extreme value theorem to be used, we have certain requirements. The first requirement is that f has to be continuous on the closed interval from a to b. And the basic idea behind this theorem is that if you will have, or f, the function itself, will have a largest value, or an absolute max, and it will have a smallest value, or an absolute min, somewhere within that interval or at the endpoints. Your formal definition is set up as follows. If f is continuous on the closed interval from a to b, those are your requirements, then for all a is less than or equal to x, which is less than or equal to b, there must exist an x value c such that f of c is greater than or equal to f of x and f of c is less than or equal to f of x. Now, it's important to note that this x value c is not going to be both the absolute min and max at the same time. It would be a pretty boring function if that was the case. But in general, it's just going to say that there exists some sort of x value somewhere on that interval, and we're just going to call that c. What I would like you guys to take a note of is the way that this is phrased, that f of c is greater than or equal to f of x. The y value at x equals c is going to be larger than or equal to all the rest of the entire function. So it is possible to have the absolute max be, say, a value of 5, and for the function to actually reach that maximum value more than once. It is possible. But we're just guaranteed by this extreme value theorem that it has to happen at least once. The same goes for your minimum value. F of c is less than or equal to f of x. We're trying to let you know that the y value at this particular x value of c is going to be a smaller y value than the rest of the entire function. This notation is what you should be recognizing, especially when we're working with multiple choice questions, or maybe some prompts within the open response questions that will be using this notation to try to hint that you're going after an extreme value theorem or you're talking about a maximum or a minimum. Our next theorem is called the intermediate value theorem. And if we just break down those words to begin with, intermediate is talking about value, or and specifically values, are talking about y values that are in between two other y values. So we talk all the time about we have a certain domain and our domain goes from A to B, but what is the range of that function based on A and B? So the intermediate value theorem is an existence theorem. It tells us that there are points that will exist that have specific y values. And those y values are going to be the values that are in between f of A and f of B. So if we look at our three graphs up here to talk about what this means, f of A right here has a value that's about 2. F of B has a value of maybe negative 1.5. So what this theorem is saying is that because we know f of A and we know f of B, and this function is continuous and closed, we know that there have to be points that have a range value in between negative 1.5 and 2. That's the part that is guaranteed for us. We can't possibly know that we go beyond 2 and negative 1.5. We can see here in the picture that this in fact does go above a y value of 2, and it does go below a y value of negative 1.5. But we're not guaranteed for that to happen if we only know the information about our endpoints. If we take a look at the second graph, we have f of A, which is up as around a value of 3, and then B, f of B, would be a value of 0. For this graph, if I only told you that f of A was 3 and f of B was 0, we would only be able to know that we have y values from 3 until 0. We would not know if this dipped below the x-axis, as we can see here. For the last function, f of A and f of B do not exist because this is an open interval. So therefore, because we don't have our endpoint values, we can't possibly know what other range values this function might contain. So this is another existence theorem in which we have to be continuous and closed to know or guarantee that we have certain points. Here's our official definition. Our requirements are that f has to be continuous on this closed interval. And the basic idea is that the graph of f will pass through all of the y values between those y value endpoints at least once. Your formal definition says that if f is continuous on the closed interval from A to B, and k is between f of A and f of B, then there must exist an x value c such that f of c is worth k. Let's draw a little bit more abstract example of how this works. Let's pretend that we know that f of A has a value in the positive y. And we know that f of B is going to have a value of 0. The only y values that we are guaranteed for sure would happen from f of A down to 0. Those are the only y values that we are guaranteed to have. Here are some reasons why that is. What could the function possibly do? Well, the function could be something that's maybe linear and just goes from f of A down to f of B, and that's it. The range of that would only be from 0 to f of A. Or perhaps f of A is not linear, but it still only goes in between 0 and f of A. All of those range values are covered, and we hit several of them more than once, but we only know we can go from 0 to f of A. Perhaps our function does something like this. If that's the case, The only y values that we are guaranteed or known to have are the ones that happen between f of a and 0. All of the other range values, we didn't know that that was going to happen, so we can't guarantee that they will be there. Our last theorem is called the mean value theorem. When we think about the word mean, it has several definitions, but when we think about a mathematical mean, we are typically talking about an average, or the idea that we're summing up a bunch of values and then dividing it by what we have. In this case, the mean is referring to our average rate of change, or that slope of that secant line. So in order for this to work, we are going to start with our f of a, our f of b, our two separate points, and we're going to calculate what the rate of change is between the beginning and end of our interval. So we would start here with f of a, we'd end up over here with f of b, and we would try to figure out what the rate of change was between those 2 points. We're essentially calculating a slope of our secant line. What the mean value theorem is going to state is that we are also guaranteed to have an instantaneous rate of change equal to that rate of change within the interval. So right here in the first graph, I have my average rate of change highlighted in red. There will be a tangent line with the same slope that happens at least once. In our first picture, that first tangent line could happen somewhere near that maximum, where our tangent line would have the exact same slope as the secant line. It would also happen again somewhere as we approach our minimum value, somewhere around there. The tangent line would also have that same slope. So in this case, it happened twice, but this theorem just guarantees it would happen once. For our next function, here's our two endpoints. This is the secant line that connects them. Our tangent line that will have the same slope may occur somewhere around that -1. And in this case, it's only one tangent line that would actually share that same slope. When it comes to our last graph, again, because we have open circles at our endpoints, we cannot make a secant line slope, and therefore we cannot make a tangent line slope to match it. So the requirements for this, because we are working with slopes and we're working with the idea of an instantaneous rate of change, we not only need to be continuous on that closed interval, but we need to be differentiable on the interior of that interval. We won't be taking the derivative at an endpoint because there are too many different tangent lines that could be drawn at an endpoint. So we're going to be looking at various points within the interval itself that we might be taking tangent lines at. So the basic idea is that at some point within that interval, the slope of your tangent line will be the same as the slope of the secant line. They're going to be parallel with each other. Your formal definition says that if f is continuous on the closed interval from a to b and differentiable on the open interval a to b, then there must exist an x value called c within that open interval such that the derivative of f at c is equal to f of b minus f of a all over b minus a. This last part is the key part for making this the mean value theorem. Your instantaneous rate of change is going to be at some value c, somewhere in the middle, will be the same as your average rate of change between the endpoints. So one example of where this mean value theorem could be applied to something a little bit more real world or a little bit more realistic is dealing with maybe collecting tolls on an interstate as drivers are passing through all these different toll booths. So let's say we have a driver that is at mile marker 5 along an interstate, and they have to pay a toll. Then the driver continues to travel, and they have another toll booth at 35 miles down the road where they pay another toll. Let's say they pass through the very first one at 9 o'clock a.m., and then they pass through the second mile marker or the second toll booth at, let's say, 9:30 a.m. The question is, was the driver speeding during this time at all? Did the driver speed along this road when they traveled from the 5-mile toll booth to the 35-mile toll booth? Well, the total number of miles that they traveled was 30 miles, and they traveled in that in 30 minutes, which we will convert to in half an hour. So using our distance is equal to rate times time. So distance over time would be our rate. And again, this is calculating an average. We had a change of 30 miles over a change of a half an hour. It's going to be an average. For us, the 30 miles over the 0.5 gives us a total of 60 miles per hour. So what we know is that on average, the driver was traveling at 60 miles per hour. It is possible that they went a little over. It is possible they went a little less. But the only thing we are guaranteed is that the driver had to have been traveling 60 miles per hour at some point between 9 a.m. and 9:30. Is that enough to justify a speeding ticket? It depends on the road and what the speed limit of the road is. But all we are guaranteed is the 60 mile per hour had to have been traveled at some time between 9 and 9:30.